we're going to look at some different graph shapes that you might see while doing physics labs. In the lab, we're always going to investigate how changing one variable affects another variable. So the variable that you are changing, that's going to be your manipulated variable, and you're always just going to have one of those. And the one that's affected, that's going to be called the responding variable, and there's also going to be only one of those. Any other variables will stay the same, and we say that those have been held constant, and those are what we call controlled variables, and you are allowed to have more than one controlled variable. So let's say that we're investigating this relationship here in the lab. So I've just put a star beside where I want you to look. So we have the formula V equals F lambda. So this letter here is the Greek letter lambda. Let's say that I decide to change lambda, so lambda is going to be my manipulated variable, and I want to see how the speed changes as a result. So speed is going to be my responding variable. F is going to be a controlled variable. Because F is not changing, I don't care what's happening to it, so we're just going to ignore F. You can pretend like F is not there. And I can write out something that looks like this. So I can write V, and then this symbol, which kind of looks like a fish, but it means proportional to lambda. And we would read this as V is directly proportional to lambda. Now, the reason I know that it is directly proportional is because when you look at lambda, it is just plain lambda. And by that I mean it's not lambda squared, it's not 1 over lambda, lambda is not under a square root, it's just lambda by itself with nothing happening to it. If you look here where I'm circling, whenever we have a linear relationship, that's always going to be the case. So x here has nothing happening to it, it's just plain old x. Whenever it's a linear relationship, we can say y is directly proportional to x, or in the case of this formula, v is directly proportional to lambda. Now, whenever we have a directly proportional relationship, if the manipulated variable doubles, the responding variable will double as well, or if the manipulated variable triples, then so will the responding variable. They sort of copy each other in that way. Now, whenever you have a directly proportional relationship, if you graph it, you're going to get a straight line. When we graph, we typically like to put our manipulated variable on the x-axis, so we'll put lambda on the x, and our responding variable on the y, so we'll put v on the y-axis. And again, because it's directly proportional, I know when I graph it, I'm going to get a straight line. Now, here we have a place for a linearized graph. We're just going to write not applicable there. A linear graph just means a graph that is straight, and the graph is already straight. So we're going to keep going. Okay, next we're going to look at a power relationship. So this time we're going to have one variable being proportional to another variable, but the second variable is going to be squared. So I could read this as y is proportional to the square of x. So let's say I want to look at the relationship between speed, which is v here, and a, which is acceleration. Let's say I decide to manipulate speed. So my manipulated variable is going to be speed, and my responding variable is going to be a with a little c next to it. Just ignore the c. Anything else in the formula is going to be controlled, and we're just going to ignore it. So I don't really care what's happening with r because I'm not studying r in this particular lab. And we can write down AC is proportional to v squared. Okay, and when I write down this proportional thing, I'm always just copying what's happening in the formula. So because it is v squared in the formula here, that is how I know that it also needs to be v squared over here. Okay, and whenever you have this type of relationship where your manipulated variable is squared in the formula, when you go to graph that, so if you put your manipulated variable on the x-axis and your responding variable on the y-axis, you're not going to get a straight line anymore. Instead, you're going to get this other shape that always kind of looks like this. I've drawn it out already. Now, because that graph is not a straight line, it's actually not super useful in the lab. It's harder to analyze. And so we want to graph something else instead that will be a straight line, because that will be easier to work with. And so to make it into a straight line, we're going to do what we call linearizing. When you make a linearized graph, you're just still going to put the same thing on the y-axis. So if it was AC up here, it's also going to be AC on the linear graph, so the y-axis doesn't change. But then on the x-axis, you just copy what's happening in the formula. So because it's v squared in the formula, instead of graphing just plain v, we're going to have v squared. So that's what I want you to notice, okay? If the variable is just plain here, then the graph is not straight. But as soon as we copy what's happening in the formula, when we go to graph that, now we're going to get a straight line. Okay, let's look at another example of a different graph shape. So here we're going to look at this formula that I'm circling. And we're going to study the relationship between f and r. So let's say that r is manipulated, f is responding. We can write it this way. F, we'll put the little g next to it, is proportional to 1 over r squared. Okay, and so because r squared is on the bottom of a fraction initially, it still has to be on the bottom of a fraction when I write out the proportionality statement. And everything else that's not fg or r is going to be held constant. So all this stuff on top, those are our controlled variables. We're pretending like they aren't there. And so that's why in the proportionality constant, I'm not writing them. I'm just putting a 1 there instead, because I still have to show that r squared is on the bottom of a fraction. So we would read this as f is inversely proportional to the square of r. And whenever we have this inverse square relationship happening, it is this graph shape here that I'm tracing over that we're going to get. Again, we're going to put our responding variable on the y-axis, and we're going to put our manipulated variable on the x-axis. Remember that when you put just the manipulated variable, the plain version, so here I'm not putting r squared or anything, it's just plain old r. When it's the plain version of the variable, the graph's not going to be a straight line. It's going to have this sort of characteristic shape. But if I want to make the graph linear, or I want to make it a straight line, then I have to change what I graph. So I'm going to put fg still on the y-axis, because remember, the y-axis isn't going to change. But then on the x-axis, I'm going to copy what's in the formula. So in the formula, r was on the bottom of a fraction, and it was also squared. So this time I'm going to put 1 over r squared there, and you would see if you had data to graph that if you graph this, you would get a straight line. Okay, next we're going to look at an inverse relationship. And this time we're going to use a formula that we used earlier today, but we're going to change which variables we're looking at. So let's suppose that I decide to leave speed constant this time. So speed is v, so let's say that this is my controlled variable. And let's say that I decide to manipulate lambda, and I'm going to measure what happens to the frequency. So frequency is going to be responding. When you are working with a formula, you should rearrange it so that the responding variable is isolated. So we're just going to rewrite this formula like this. F is going to be v over lambda. And the reason we're doing it that way is it makes it easier to write out the proportionality statement, because whatever's going to go on the y-axis, which is always going to be your responding variable, should be by itself over here. So if we're looking at the relationship between f and lambda, the relationship looks like this. Okay, so lambda is on the bottom of a fraction, so we're going to keep it there in the proportionality constant. V is constant, so I'm sort of pretending it's not there, which is why it just is a 1 here. So here I would say f is inversely proportional to lambda, and this is an inverse relationship. And whenever we have an inverse relationship, it's always going to look kind of like this. This shape looks almost the same as the last one. They are slightly different, but we won't worry about that. And if we graph this, So we're going to have f on the y-axis and then just plain old lambda on the x-axis. Again, that's not a straight line. So if we want to end up with a straight line, we have to linearize the graph. And I want you to think for yourself for a second, if I want to get a linear graph, what has to go on each axis? So remember, the y-axes of both graphs are the same. So f is just still going to be f on the y-axis of the linear graph. But to make a linear graph, instead of putting the plain version of the variable, you match what is happening in the formula that you are investigating. And in the formula, it's 1 over lambda. So x is going to be 1 over lambda. And when we graph that, it is going to be straight. Okay, last one. So now we have what's called a root relationship. And so we're going to look at this formula here. Okay, we're going to make our manipulated variable for this particular lab L, and we're going to make T our responding variable. Now, why did I pick those two? Not really any good reason, okay? It's just that happens to be the lab that I am doing. And anything else in here is just, we're gonna ignore it. So we're gonna ignore the 2 pi, and we're gonna ignore the g. Now, when we graph this, so if we put t on the y-axis and L on the x-axis, because the relationship is this, t is proportional to the square root of L, right? Because L is under a square root in the formula. So when I write out my proportionality statement, L still has to be under a square root. This is not a directly proportional relationship, right? Because it's not just plain L, something is happening to L. And so this is what we call a root relationship instead. And whenever you have a root relationship, you're going to get sort of this shape here that I'm tracing over. And if we wanted to get a straight linear graph instead, remember, keep the y-axis the same. So we're going to put t on the y-axis. And then on the x-axis, we're going to copy what's happening in the formula. So we're going to put square root of L, and that would end up being straight.